exponential fields.
So I'd also like to thank the organizers for having me. Anytime I can go to a place where there's free coffee all the time, I'm very excited. So this is joint work with Paolo D'Aquino, Julia Knight, and Selma Kuhlman. And at the end, I'll be talking about, or intermixed, I'll be talking about exponential integer parts. But really, I want to give you a sense about the difficulties for computing these integer parts wherever they are, I'll tell you. And what I mean for computing for me, I'm talking about computing in Turing degree sense. So, okay. So really, we're going to be working in the setting of real closed fields. So real closed field is just a model of the first order theory of the reals. So we're thinking about the reals as an ordered field. Right? And an integer part for an ordered field, it's just something that sits inside the field, just like the integers sit in the real numbers. Right? So in some sense, it's a skeleton. It's going to be a discrete ordered subring, I, such that for any element of the field, R, there exists some little I, such that R is between little I and I plus 1. Okay? And of course, well, if we're talking about an Archimedean field, Z is going to be, the actual Z is going to be the unique integer part of R. So throughout this talk, we're not interested in that case. We're only interested in non-Archimedean real closed fields. So it's an old theorem of Morgan-Rasser that says that every real closed field R has an integer part. Right? So I should say this is not the best result possible. You can decrease real closed field by a little bit, but you do need a lot of that closure under certain kinds of roots to be able to get this result. So this is probably the most sort of easy to deal with statement for where you have integer parts. But you can back down a little bit from total real closure. Right? But whenever I see such a statement, I'm interested in, well, how hard is it to compute one of these guys? Right? It's also interesting, integer parts come up with weak fragments of arithmetic. So IOPEN is the subsystem of a piano arithmetic, which throughout I'll just call PA, where induction is restricted to quantifier-free formulas. All right? And it's 1960s, Shepherdson showed that if you've got a discrete ordered ring I is a model of IOPEN if and only if I is an integer part of some real closed field. Okay. Recently, as the last speaker was saying, it is fun to go and see what people have been talking about before. Recently, there's been a lot of interest in the question of when does a real closed field R have an integer part which actually models full piano arithmetic, or various fragments of it. So it's fairly recent, maybe 2 years ago, D'Aquino, Knight, and Starchenko showed that if R is countable, the answer is if only if R is recursively saturated. And recently, Dave Marker pointed out that the countability condition is actually necessary. There are uncountable recursively saturated fields without integer parts modeling PA. But then I saw a previous talk in February. Carl gave a talk showing that if R has an integer part modeling PA, then R actually has some kind of left exponential function. If you don't know what that is, that won't be important now in this talk, but it's sort of got a partial exponential function going on. So currently this research is working towards understanding. These bottom two theorems are working at getting a characterization of when you have an integer part modeling PA in the non-countable case. And that's what this last theorem is getting towards, but there is not a characterization yet. So that will be one of the questions that I'll be working with Kuhlman when I see her in a few weeks. Okay, but even though I mentioned the word exponential, I want to talk about or end with talking about real closed exponential fields. All right? So an exponential real closed field, well, now we're going to add on, in addition to the ordering in the field structure, we're going to add on a 2 to the x. All right? And you'll see why we care about 2 to the x in a second. Well, okay, it's such that R is a real closed field, and the 2 to the x behaves the way you think it would if it was an exponential function. So that includes the 2 to the x plus y is equal to 2 to the x times 2 to the y, but also having logs. I'm expecting that all my positive elements will have logs. All right? And there's some growth axioms there as well. Well, if you think about it, if you've got a real closed exponential field like the reals, if you take 2 to any positive integer, you get another integer, another positive integer. So that's all we mean by an exponential integer part. It's an integer part which also has that property that for any little I in I, if I is positive, then 2 to the I is also in the integer part. Right? And so Racer, again, an old theorem, he showed that if you've got an exponential real closed field, then R has an exponential integer part. Okay, so today, so what am I really interested in? Well, I want to look at these two theorems, or I've been looking at these two theorems for a while. Every real closed field has an integer part, and then Racer's strengthening or generalization, if R is a real closed exponential field, then it has an exponential integer part. It's very clear the second construction builds heavily on the first. So it's certainly the second one's going to be a lot harder than the first one, but we're trying to get a sense of where the complexity of either of these theorems lies. So I'm going to start by just saying a little bit about how Morgan and Racer go about showing these integer parts exist. Lucky for me and lucky for us, it's a constructive proof. It's highly constructive. So I'm going to give you an overview, but I will tell you what these objects that I'm not telling you what they are. I'll get back to those later. But just giving you a big picture of how they do this, what they did is they looked at some generalized series called KG, and they observed that this field of generalized series has many subfields with simple integer parts. Okay, so I'm leaving all of that for later. And then what they do is they build an embedding from any real closed field into this field of series so that the image is one of these nice subfields. Right? Well, of course, once you've got an embedding, you've got an integer part over here in the series field, well, you just pull it back to R. Oftentimes I'll call the image under this embedding of any element the development of that element, right, rather than series. Okay. But in order to define, I want to tell you what this KG is. I need to tell you what K and what G are. So what's going on here is we've got an Archimedean valuation on the real closed field R. So if you've got two non-zero elements, well then I say that X is Archimedean less than Y if there's some natural number, multiple of Y, gets you above X. Okay? So two elements Archimedean equivalent if it goes in both directions. And then if you take your non-zero elements of R and you mod out by the Archimedean equivalence, you get what's called a value group. Right? And of course this natural projection turns out to be a valuation on R. Now I'm going to think about, yes, this is cosets. My value group consists of cosets. I'm really going to think about the value group, a section of representatives for the value group that actually lives inside the real closed field R. It's just easier to build with it. So then you can think of this G as, it's an ordered group. Its operation is inherited from the real closed field under multiplication. Right? And the ordering, I'm keeping the same. I'm saying that, okay, if your valuation of X is less than or equal to valuation of Y, if only if X is Archimedean less than Y. And so it's a fact, since R is real closed, the value group G is going to be a divisible ordered group. But just to give you an example of what one of these things looks like, let's take one of the simplest non-Archimedean fields out there. Say that you've got some element A, which is infinite in the Archimedean sense, so it's just larger than any natural number n. Then the value group of just the real closure, just take the smallest real closed field containing Q and this new element A, well, the value group is going to be isomorphic to A to the Q. A is an infinite element, all right? But then, once you have A is infinite, well, A squared is going to be even more infinitely larger. Since it's real closed, you get closure under those roots. And so that's why it's A to the Q for Q's in the rationals. So certainly, taking A to the 0, that gives you 1. That's the identity of our group because we're thinking about multiplicatively. So those are all elements, or we're thinking about 1 as representing the finite elements, the elements which are Archimedean equivalent to 1. All right, so in order to say what the K was, so that's our G. We've defined the value group. the k is the residue field, which is simply the quotient of all finite elements, so all elements in R which have finite valuation, modded out by the infinitesimals. So the residue field really just encodes what elements of the real numbers are living inside your real closed field R. So in this example, well, if you just adjoin A, an infinite element, and to the field Q and take the real closure, its residue field, I mean, it's not just isomorphic, it is the real algebraic numbers. Right? So you can sort of think of the value group G as saying what magnitudes of infinity exist in your field, and the residue field K is saying what reals are present, what finite elements are actually present. All right. Okay, so finally I can say what KG is. This is where Morgan-Rousseau are embedding any real closed field into. Right? So if you've got a real closed field R with a value group G and a residue field K, then K bracket bracket G, it's just going to be formal sums where the terms consist of the AIs are just going to be elements of the residue field, and the GIs are coming from the value group. And the last thing, of course, is we expect that they behave like regular power series in the sense that G0 should be greater than G1, greater than G2, and so on. Why they're general? Well, it's because now they have ordinal length rather than just, say, length omega. The support of any one of these developments is just all of the G's that have non-zero coefficients. And I'll often use this notation here of just kg greater than 1. We talked about how 1 represents in the value group really the finite elements. So the elements greater than 1 are going to be the infinite elements. So kg greater than 1 are just all of the series or all of the developments with all infinite support. Okay, so now that we've said what kg is, I said that what Morgan-Rousseau noticed was that if you've got a real closed field, we're going to embed it forward into these kg's, but we want that the image is somehow nice. Well, niceness is just going to be in that when you map forward, the image is going to be truncation closed. And all that means is what you would expect it to. If you take any series, say I've got T up there, one of the series in F, well, its truncation to some lower level ordinal length is just chop off the tail of the series, chop off the end. And we say that a subset of kg is truncation closed if all truncations of any element or F stay inside of the field. So what's the point? Really, the point is that if F is a truncation closed subfield of kg, of these generalized series, then we have a very easy to compute integer part. Just think about in grade school how you would, they used to make you practice, rounding, finding the integer part of a number. What do? You chopped off the decimals and you rounded to the next integer. Well, that's exactly what they observed. They observed that, all right, if I've got a truncation closed subfield and I want to find the nearest integer part, chop off all of the infinitesimal places, okay, and round to the closest integer. So that's what this notation means. It means that if F is truncation closed, then IF, which is just take all of the series in F, which have all infinite support, and add on integers, that together will form an integer part. So what Morgan-Rousseau, their theorem, was showing that you could build one of these embeddings. So they can build an embedding delta, which goes from R into kg, and so that the image is truncation closed. And then you get your integer part that way. All right, so that's just the basic construction. Well, how do you do this algorithmically? I won't spend too much time here, but you're going to do it by induction. You well order all of the elements in R, and you're going to build this embedding by making sure that you define the embedding on one element at a time. Essentially, really, how do you define what delta the embedding is? It's really going to be a power series expansion over what you've done so far. So it really is sort of like taking Taylor series over what you've got so far. So it's just an induction. All right, so going back to my motivations, what we really wanted to answer, well, I still really like to answer is, if I have a computable real closed field, how hard is it in the Turing degree sense to compute an integer part for that real closed field? And of course, since we have this constructive proof, we say, hey, let's analyze the proof, see how bad it is, go from there. Well, it turns out, and I proved this with Knight, turns out that the lengths of these power series, even when you're talking about just a nice, countable, real closed field, okay, the lengths can get really long, right? So they certainly can get at least omega to the omega to the omega, which I like omega by itself without the tower going on. So the lengths are really long, and that really blows up Turing degree complexity. If you were just going to run this construction, you know, and sort of just count how many jumps of the halting problem you're doing, it looks kind of bad. We don't know if this result is sharp. We conjecture that that's as long as they should get, as long as that you've got a omega length well-ordering of your real closed field. But that's something that we're still working on. We thought we knew how to prove it, but we had a mistake in our proof. All right, so then, since it seems hard to do what Morgan Mercer were doing, we said, let's try and find another proof. We know that some oracle is needed. Specifically, we know that the problem of finding an integer part can at least code the halting set, but we don't know if the halting set in general is sufficient. So that's very low level computability. Right? So what we were able to do was able to show that Mercer's construction for exponential integer parts is highly complex. Right? So at least we could show something. And highly complex, meaning that it can't take place in a reasonable computational setting. Well, what do I mean here by reasonable? Our setting is going to be the least admissible set containing omega. So we're way out of where I would say, I like the arithmetical world. But in case you're not familiar, as I wasn't originally, this isn't my favorite place to be, an admissible set, well, it's a transitive set. You know, we're thinking a model of set theory. And it satisfies the axioms of ZF, right? But it doesn't have any power set axiom, because we're trying to restrict what sets exist. And the axioms of comprehension and replacement are restricted to delta 00 formulas. Okay. So why this setting? Well, admissible sets generalize the standard setting of computability. They're sort of the next place to go after saying something isn't arithmetical, because all of the subsets of omega in L omega 1 CK are exactly the delta 1, 1 sets. So exactly the hyperarithmetical sets. So sets which are computable from some computable ordinal number of iterations of the jump, essentially. All right. So exponential integer parts. Well, what did Mercer have to do in order to show that any exponential real closed field has an exponential integer part? Well, he noticed this odd property. He noticed that if he could build an embedding, which he already knew how to build embeddings fairly well, he noticed if he could add on an additional property he called dyadicness. So the property that he needed that would suffice would be if the development of an element y in the real closed field had all infinite support. Well, that should happen if and only if 2 to that element, was also in the value group. So here what he's doing is now his embedding, before, in some sense, the embedding doesn't care so much exactly what G looks like, what section of G you're looking at inside the real closed field. Here, now he's coding in things into the section for the value group as well. And it's fairly easy to see that this odd condition of dyadicness, of saying, okay, well, if you map to an element with all infinite support, then 2 to that element must be in the value group section, then you get an exponential integer part. Well, why? So, well, say you've got an element of your integer part that you get from pulling back the embedding, from that truncation method of constructing an integer part we saw before. So if you have a positive element, little I, in your integer part, well, then it consists of 2 pieces. It consists of r plus z, where r maps to something with all infinite support, and then plus z, plus an integer, okay, because we just chopped off all the infinitesimal pieces and rounded up. Right? The interesting case is where r is positive. Right? Well, since r is positive, you know that by how we constructed the integer part, we know that it maps to something with all infinite support. That was just by definition of how we constructed this integer part. Right? So 2 to the I, well, by definition, 2 to the I is equal to 2 to the r plus z, which is equal to 2 to the r times 2 to the z. 2 to the r, we just said that r maps to something with all infinite support. Well, by this dyadic property up there, that means that that 2 to the r is an element of the value group. Right? 2 to the z, well, I don't know what it is, but it's a rational number. It's in the residue field. So this thing, this 2 to the r times 2 to the z, is just a monomial where the 2 to the z is a residue field element, and 2 to the r is just a value group element. So that's also an I because it's infinite. It's an infinite monomial. So what we showed, so I won't talk about how constructing the dyadic delta changes things, but essentially what it does is it adds another loop of induction. Before there was sort of easy induction step by step by step. But now this new property of dyadicness creates sort of another loop of induction each side, each level. Right? So that extra loop allows us to show that this construction cannot take place in the least admissible set containing omega. So what we showed there is an exponential real closed field. Right? We can well order it, well ordering which isn't too bad, omega plus omega, but that's not so important here. Right? It's got a residue field section, the well ordering, and the residue field section. All of the pieces, all of the inputs to this construction all live in the least admissible set. They're very simple, actually. They're all arithmetical. I mean, really easy. But Serre's construction of this embedding, and hence of the integer part, cannot be carried out in L omega 1 ck. All right, so in the least admissible set. So what goes wrong here? Well, we actually don't totally know, because how you show that this is broken is using bar-wise compactness. So it's a compactness argument, and so you really can't say which piece breaks. Either the lengths of the developments get longer and longer, and that they need ordinals outside of the least admissible set, that they need non-computable ordinals. Or the length of one of these inductive chains goes out, uses some non-computable ordinal, because the least admissible set only contains the computable ordinals. So I hope I've given you some flavor for where building these things are difficult, and also some of the other sort of connected questions that are related to integer parts. So thank you very much.
Questions, comments? I have one, but I don't know that I want to go first. So, the construction, what is an upper bound of the construction? I mean, if you're doing these ordinal inductions, one might speculate you could do this in pi1 comprehension or something.
Yeah, so to be honest, I haven't looked at it. I mean, I can say it's constructible, but that doesn't, say anything. But I haven't looked beyond there. To be honest, we were kind of, once we realized that this was, to me, this is really bad. So I think after this, we kind of went back to the integer part, just the sort of without the exponential, and we're trying to get something there. But that would be something to look at.
Well, to me, that's really interesting.
Exactly. No. Exactly. It's more that I'm less familiar with the.
But it might be that there is a simpler proof and therefore a simpler construction that doesn't need.
Exactly. And that's really what we're looking for. Is just any kind of simpler ways to get these. And that's where the other results that I was mentioning are interesting in the sense that this construction, z is always a direct sum end of the integer part. So that really limits what kinds of models of arithmetic you can realize using this construction. So that's sort of a general big question. Okay, well, what if you want to build a particular kind of model of arithmetic? Try and build that instead. But you're right, that's exactly
Any other questions? No. Okay, let's thank Aaron again.